Hi. So today we're gonna talk about ecological issues and applications on human consumption. First is thermodynamics. Thermodynamics is the study of the effects of work, heat, and energy on a system. Thermodynamics is only concerned with large-scale observation. The first law of thermodynamics is that any thermodynamic system in an equilibrium state possesses a state variable called the internal energy. Between any two equilibrium states, the change in internal energy is equal to the difference of the heat transfer into the system and work done by the system. The second law of thermodynamics is that if you are constrained to put your water wheel halfway up the waterfall, then you can extract at most half of the available energy. The third law of thermodynamics is that absolute zero is a temperature that an object can get arbitrarily close to but never attain. For example, temperatures as low as 2.0 times 10 to the negative 8 K have been achieved in the laboratory, but absolute zero will remain ever elusive. There is simply nowhere to put the last little bit of energy. This is the third law of thermodynamics. It is impossible to lower the temperature of an object to absolute zero in a finite number of steps. The sun is a primary source of energy for living organisms. Plants trap this energy from the sunlight and undergo photosynthesis, effectively converting solar energy into chemical energy. Photosynthesis is a process used by plants and other organisms to convert light energy into chemical energy that can later be released to fuel the organism's activities. In these light-dependent reactions, some energy is used to strip electrons from suitable substances such as water, producing oxygen gas. The primary producers of our planet includes plants, lichens, moss, bacteria, and algae. Primary producers in a terrestrial ecosystem live in and around organic matter.
For this part of the video, we will be learning about an aquatic environment's dependence on nutrients and light. Now keep in mind that the example we'll be using here is a lake ecosystem. Other aquatic habitats may slightly differ in some aspects. Here we see a lake, a lentic freshwater aquatic ecosystem. It looks quite serene right now, but there's actually a lot of activities at work in it at the moment. Let's take a closer look, shall we? Fascinating. All these creatures living and thriving in the lake, hidden from plain sight. Oh, what's this? The phytoplankton are photosynthesizing. They're making use of sunlight and produce oxygen as a result. And we see that they don't produce the same amount at every depth. They vary. Their gross production is most efficient at intermediate depths and then decreases as we go deeper. This is because photosynthetically active radiation, or PAR, steadily declines exponentially with deeper depths. This means that they produce less oxygen at deeper depths. Meanwhile, the animals living in these waters respire at the same rates, at all depths. At some point, the decline in gross production and rate of respiration will be equal at a certain depth, a depth we call the compensation depth. So that's how sunlight affects a lake ecosystem. So how about nutrients? You see, when a nutrient, say phosphorus, gets loaded in the water from nearby terrestrial ecosystems in a process called allochthony, the phytoplankton in the lake make use of that phosphorus, growing more rapidly and producing more oxygen in the process, increasing the lake's net primary production. In addition, organic carbon is another important nutrient that an ecosystem needs. There are two ways aquatic ecosystems acquire organic carbon. One is autochthony, where the carbon comes from inside the ecosystem. And two, as mentioned before, allochthony, where the nutrient comes from an outside source or different ecosystem. Which process dominates in an ecosystem varies depending on the availability of shade and sunlight. You see, in big lakes, where the area is mostly hit by sunlight, the phytoplankton can produce the organic carbon for the ecosystem. Whereas in small lakes, where the trees mostly shade the lake from sunlight, the phytoplankton cannot grow and initiate production, and so they obtain their organic carbon from the adjacent terrestrial ecosystem from dead organic matter in the form of dissolved organic matter or DOM or particulate organic matter or POM.
Plants allocate carbon to plant growth. It is a positive feedback system. The greater allocation of carbon, the greater net carbon gain in plant growth. Decrease of NPP and precipitation is the result of the change of carbon allocation of plants within the ecosystem. Decrease of precipitate allocated growth to roots rather than leaves. Different ecosystems have different patterns of carbon allocation relative to individual plants where it is based on different environmental gradients. Greater NPPs mean that they have greater standing biomass seen in both terrestrial and aquatic environments. Larger plants compared to smaller plants have a greater net carbon gain or absolute growth rate. However, this is not often the case when we examine the relative growth rate and collective growth of plants. There is an inverse pattern between RNPP with standing biomass in terrestrial ecosystems where grassland ecosystems have higher NPP than forests. Production is relative to time and age within an ecosystem. When photosynthesis and growth is affected by seasonal variations and environmental conditions. NPP also varies with stand age when forests and shrubs live for a long time, influencing allocation of energy. The leaf mass supplies less energy to support the biomass. Energy is allocated to maintenance and support, which increases as the plant ages. As stand ages, there is a decline in photosynthesis and respiration. The pattern is an increasing productivity in early stages and declines with stand age.
Now for the next topic. We will see the relationship of primary production and its direct effects on secondary production. The energy available to the heterotrophic component of the ecosystem is dubbed as net primary production, and this is affected by many environmental factors as well as interactions within the ecosystem. Energy, when ingested, is used in metabolism, and in the maintenance and preservation of an organism's bodily functions and conditions. All remaining energy, however, is eventually lost to the heat, and whatever remains goes into production of new tissues or allocated to reproduction of offsprings. This energy allocated is called as secondary production, which represents the formation of living mass of heteroorganisms over a period of time. Secondary production is dependent on primary production, in the sense that primary production sets a limit on secondary productivity within an ecosystem, thus maintaining a stable and balanced relationship. We now move on to the variety of efficiency and energy production. Although it is established that there is a general relationship between primary productivity availability and consumer productivity, within a thriving ecosystem there exists a variable efficiency in transforming energy among consumers. The assimilation efficiency is a measure of the efficiency with which the consumer extracts from food. On the other hand, the production efficiency is defined as the measure of how efficiently a consumer incorporates assimilated energy to secondary production. In the case of endotherms, they exhibit high assimilation efficiency but low production efficiency due to the high expense of energy on respiration, while ectotherms display the complete opposite due to the low rate of respiration allowing them energy. A common lesson in ecology since our early years in education is about food chains and the resulting energy flow. Various members of a food web can be classified into categories of eutrophic organisms or feeding levels, wherein autotrophs occupy the first level and heterotrophs that feed on them are on the second level. Subsequently, carnivores that feed on herbivores are up on the third level. Energy flow in ecosystems tend to take two routes. One through grazing food chain, the other through the detrital food chain. Now the bulk of production is used by organisms that feed on dead organic matter, and these two food chains are linked by the input of dead organic matter and wastes from the consumer food chain functioning as input into the detrital food chain.
The energy flows through trophic levels can be quantified. Some portion of energy available was consumed, while partial of this energy was absorbed by the individual. The remaining energy will become waste products. The absorbed energy will then be used for sustaining daily respiration. Then come up with a product. During this process, a large amount of energy will be wasted or used. Only a small portion of consumed energy will finally become a product. For example, if the available energy for grazing herbivore is 1000 kilocalories, 200 of it was consumed. In this 200 unit of energy, only 70 has been absorbed. The rest was excreted as waste products. Then 56 out of 70 kilocalories of the absorbed energy was used for sustaining respiration. Then the remaining 14 kilocalories of energy will finally become the product that produced by the grazing herbivore. Since all organisms require energy for respiration, a huge amount of energy will be lost when the energy is passing to the next level. For instance, if the energy taken by the producers is 100%, only 10% of the energy will be passed on to the next level, which are the primary consumers. Then this amount of energy will be utilized again in respiration. 10% as well of this amount of energy, which is 1% of the original amount, will be passed on to the secondary consumers. And so on to the tertiary consumers, like us humans. We are only taking 0.1% of the original amount of energy.
And we would like to give thanks to the following references and journals that helps us succeed our research. Thank you guys for listening.